The other characteristic of psi, or the stream function, is that psi is constant or remains constant over streamlines. So, you know, the streamline is a curved line that the velocity vector is tangential to it at any point, at any time. It can be proved that the magnitude of the stream function remains constant along one streamline. What differs from one streamline to another? The other characteristic of the stream function is that the volumetric flow rate, since the flow is incompressible, we may use the volumetric flow rate, Q, is equal to the difference of the magnitude of the stream function over each streamline. So we have two distinct stream functions. The magnitude of the stream function over the first streamline is psi 2 and the other one is psi 1. If you subtract these two quantities, it will yield the volumetric flow rate between those streamlines. Also, we have another definition of the stream function, which is called the Stokes stream function. The Stokes stream function is the axisymmetric version of the stream function, and this relation changes to this one. If the flow geometry is axisymmetric, the volumetric flow rate between two stream surfaces or stream tubes is 2 pi times the difference of stream functions over those stream tubes. The other characteristic of the potential function is that the lines of constant phi or constant potential function and the lines of constant psi or constant stream function are normal to each other. You can compute the magnitude of phi and psi and find the lines over which the phi is a constant and the psi is a constant again. You can easily obtain that the phi iso stream function lines and iso potential function lines are perpendicular to each other. And finally, the other characteristic of these two important scalar functions is that we use them to simplify the solution procedure. It means that if we use directly the velocity, you know the velocity is the key parameter in fluid mechanics, but using these two definitions, instead of computing two unknowns, which are the velocity components, you can only compute one unknown, which is the stream function. Finally, after computing the psi value, the stream function, you can easily perform the derivation procedure and easily compute the velocity vector. Here again, if the flow is three-dimensional, instead of computing three different velocity vectors, you can easily compute just one unknown, which is the potential function. And after computing the potential function, for example, using the Laplace equation or any other equation, you can easily compute the derivation procedure and very simply compute three components of the velocity vector. And the last point here is that you see here we have two definitions for these two important functions. Ignore the third one. We have the velocity, the very horizontal velocity here, and again another definition for the horizontal velocity. So you can see the partial derivative of psi with respect to y is equal to the partial derivative of phi with respect to x. And similarly, the partial derivative of psi with respect to x with a minus sign is equal to the partial derivative of phi with respect to y. These equations, these relations, are exactly similar to the Cauchy-Riemann conditions in complex number theory. Then if you have the real part of a complex number and you're going to find the complex part, you have to use the Cauchy-Riemann conditions. These are exactly the same as the Cauchy-Riemann condition. This is inspiring for us to construct a complex number shown by f as a function of z. Z is composed of two geometric coordinates, which is again a complex number. The real part of this function is phi, or the potential function, and the complex part is the string function. It can be easily shown that if you want to compute the velocity component in two-dimensional space, of course, you can easily compute the derivative of f with respect to z. So, as a complex number, if you want to compute the velocity vector using potential or string function, you may use these definitions, or you can construct a complex number here with respect to z, and take the derivation process with respect to z again, and the real part of this complex number is the horizontal velocity, and the vertical and the complex part of this complex number is minus vertical velocity.